Okay, so good morning again to everybody. Today, as you can you hear the trumpets and the drums and the excitement in the air, the fireworks? Today we start the definition of the limit, which we've been all waiting for. Okay, so before I write the actual definition, which I have written before, I want to show what's going on, to try to. And I'm going to write the definition and discuss it and write it again and discuss it again. We're going to spend some time getting to know each other, okay? Because this is the most important definition in this course. So, we know functions. We know many properties of functions. We know what functions look like. We know graphs. So here's the situation we're facing. We have a certain graph of a certain function. Maybe it looks something like, let's say, something like this. Okay? And at some point, maybe the point here, let's call this point A. Want the picture to be big. So this is going to be the point A, and the one thing we're not going to care about in this definition is the value of the function at the point A. In fact, maybe the function is not defined at A at all. We don't care. That's the one thing this definition doesn't care about. So I'm gonna express that by making this absurdly big hole there in the graph. And the phenomena that we want to capture is what happens when we get closer and closer to A. Okay? When we get closer and closer to A, I'm doing this with my fingers, closer and closer to A, what happens to the function? What happens to the values of the function? So you can see from the drawing that the values, when we get closer and closer to A, the values get closer and closer to this value here. Do you see that from the picture? Okay, this is, of course, not a general picture, but just a picture. So this value here, which is not the value of the function at A, because that we don't know and don't care about, but what we can say here is that as we get closer to A, the values of the function get closer and closer to this value L. Do you agree? Okay? So this is the notion we want to define. This is the notion of a limit. That's what this L stands for, limit. And the statement is that the values of the function tend to L, or approach L, as the values of x tend to A, or approach A, or get closer to A. That's the notion of a limit. Okay? Doesn't seem that exciting, or why is that so fundamental in this course, and why did we take all that time in the introduction to build up to this notion? But it turns out that when you want to define this formally, remember all the properties that we had for functions so far, there was the intuition. We can all imagine what it means for a function to be increasing, for example. Okay? But then there was a formal definition. For x2 greater than x1, f of x2 is greater than f of x1. Remember? Or being even. We can all imagine being even as symmetric about the y-axis, but then there was a formal definition. For any x, f of x equals f of minus x. Okay? So we want to formally define this property here. And the difference between this and all the other properties we had so far is that this is not a still photo. This is something dynamical. Okay? This is a video. Okay? This is as x approaches A, the values of the function approach L. There's motion here. Do you see that? Okay, it's not that something happened. It's something that happens as we progress in time or progress in the x's in some sense. Okay? And you can try various ways to formalize this limit concept that I think is very clear from the picture what we want to say. And most people, definitely myself, would have tried to formalize it in the following way, to say, okay, as x approaches a, the values of the function approach L. But wait, that's not a definition, because we're defining something using the words we want to define, right? We want to define the concept of a limit. We want to define what does it mean to approach. Okay? So we can't define it using the word approach, or using the word gets closer to, or using the words tends to, or things like that. We have to somehow define it more precisely without using the concept itself. So, okay, we can still do that. We would maybe try to say, okay, we know what epsilon neighborhoods are already, remember? Okay, so we can say, okay, if x is in a neighborhood of A, if x is in a neighborhood of A, that's my way of saying x is close to A. If x is in a neighborhood of A, then f of x is going to be in a neighborhood of L. Do you agree that that is something more precise, that does not use the word approach or limit or tend to or things like that? Okay? We could say that. That's what I would have tried saying naively. And if x is in a neighborhood of A, we know what a neighborhood is, we defined it, right? It's an open interval centered at A with some given width, right? If x is in a neighborhood of A, then f of x is in a neighborhood of L. That's saying that for x's close to A, the f of x's are close to L. Right? Sounds good, doesn't it? I mean, I would buy it for naively. And it turns out that this naive definition doesn't work. You need something more sophisticated and surprising the first time you see it. Okay? And the sophistication is hidden in... So what we try to do is say something is happening on the x-axis implies something is happening on the y-axis. When x is in a neighborhood of A, f of x is in a neighborhood of L. So it's x phenomenon implies y phenomenon. That's kind of the idea of what we try to define. And it takes more to actually pin down this definition more precisely. So it will work for whatever we want to do with it, and that's basically everything we do from this point on in this course and in the subject. I know that some of you have questions already. Please give me a few minutes before I start taking questions, because I'm going to answer many of them. Okay, so let me babble for a while and say things in many different ways, in many different viewpoints, and then I'll give you time to ask. Okay? So, the more precise definition, the one that actually is going to work, and it's due to several mathematicians apparently came up with it in various degrees of accuracy and started using it and introduced it. And the three names that are mostly quoted as fathers of this definition are Karl Weierstrass, Bolzano, and Gauss. Okay? Not Gauss, Cauchy, sorry. Cauchy. And so Bolzano, Weierstrass, and Cauchy. And here's the definition. So here's the formal definition. Let f be a function defined near the point A, and I'll emphasize that maybe not at A itself. So I'm allowing the function not to even be defined at A itself. That's this hole in the drawing. Hold the questions. Hold the questions. We say that the limit of f is L as x goes to or approaches or tends to, the terminology doesn't really matter here, as x goes to A. And in parentheses I'll write, this is how we denote it. The limit as x goes to A, x arrow A, of f of x equals L. That's one way to denote this long statement. The limit of f of x is L as x goes to A. That's one way of writing it down. Or another way of writing it down, the same thing, and we'll use both notations in this course. Or f of x, long arrow, goes to L as x goes to A. Both notations are acceptable and used a lot. If, now I have to say what the definition really is. Okay? And here it is, and we're going to say it, draw it, say it again, draw it again, make some remarks, look at the picture again, and then take questions. If for any epsilon greater than 0, for any epsilon greater than 0, there exists a delta greater than 0 such that x minus a in absolute value is less than delta, implies f of x minus L is less than epsilon. This is it. Well, almost it. I'm going to add something tiny over here in a second. But this is almost it. Okay? Let's decipher it. Let's try to decipher what's written here. So all this beginning up to this if is just what I'm trying to define. I'm trying to define what's going on in that picture. I'm trying to define as x gets closer to L, as x goes to A, f of x goes to L. That's what I'm trying to define. Let's go back to the picture and try to decipher these notions. Maybe before we do that, I want to, in blue here, underneath these two facts, rewrite them for you. Remember property number 8 of the absolute value? Okay? Don't write in your exam property 8. It's not something well defined. Just for us it was number 8. That's my way of reminding it to you. What did it say? Saying that something in absolute value is less than delta is the same as saying that this something is between delta and minus delta. Remember that? And that's the same as saying, if you add a to the inequality, this thing is the same as saying x is between a plus delta and a minus delta. This thing and the blue thing underneath are precisely the same. Does everybody agree to that? This is crucial in understanding this definition. Everybody? Likewise, saying this is the same as saying f of x minus L is between epsilon and minus epsilon. Adding L to the inequality, we get f of x is between L plus epsilon and L minus epsilon. So I just replace these statements in blue with something which may be more easy to relate to when we go back to the drawing. Okay? So let's go back to the drawing and see what just happened here. And you have to, of course, keep looking at the definition as we discuss it on the drawing. So, remember, our naive attempt at defining this notion was to say, please look at this board. Our naive attempt for defining this definition was to say, for x's close to A, f of x's are close to L. Please look at this board. For x's close to A, f of x's are close to L. X-axis, y-axis. That was the naive attempt. What this definition is telling us, wait, start on the y-axis. For any epsilon, the life of epsilon is happening on the y-axis. Okay? For any epsilon, let me draw it. For any epsilon, so this is going to be epsilon, this is going to be L plus epsilon, and this is going to be L minus epsilon. For any epsilon, there exists a delta. Delta lives on the x-axis. It's related to the x's, not to the f of x's. Do you see that? There exists a delta, and look at the picture now. Don't try to draw it. Just look at it for a second, so you can see this. So you can see the dynamics of things. I trace this epsilon neighborhood of L until I hit the graph. Likewise from the top. Once I hit the graph, I go down to the x-axis. There we go. This is going to be my delta. Okay? So this is going to be A plus delta, and this is going to be A minus delta. So I started at the y-axis, prescribed an epsilon, said, for any such epsilon, there exists a delta, there it is, such that if you take x's in this delta neighborhood of A, so that's the statement x is between A minus delta and A plus delta, or the statement x minus A is less than delta, then f of x, let's trace f of x, there it is, f of x is going to land here, between L plus epsilon and L minus epsilon, from the way I constructed it. Okay? So, for any epsilon, there exists a delta such that if x is in the delta neighborhood of A, f of x is going to be in the epsilon neighborhood of L. Okay? Y-axis, x-axis, y-axis. That's kind of the vague idea. Y-axis, x-axis, y-axis. So I kind of went like this, went down, and then said, okay, now you're guaranteed, if you're here, if you're an x here, going up, you're guaranteed to land in this epsilon neighborhood of L. Okay? So maybe in more informal words, the way to say that is, if you want to guarantee being epsilon close to L, you need your x. If you want to guarantee that f of x is epsilon close to L, you need x to be delta close to A. Okay? So this is kind of the idea. Let's go back to the definition a second. There are two key words here. Two key words. Well, I didn't write them as words. I wrote them as symbols. There are two key symbols. This is the first one. Or maybe this is the only one. Maybe this is the key symbol. This for every. Okay? Why is it so important? Why am I emphasizing it? Because just the drawing as I drew it doesn't exhibit something dynamic. It's fixed. Back to the drawing, take an epsilon. There exists a delta. If x is here, f of x is here. That's not really dynamic. But this is true for any epsilon. Now if you take a smaller epsilon, maybe a small tiny red epsilon, let's find a good red thing, there we go. Now take a smaller epsilon, maybe an epsilon this big. Can you see this? And now this is L plus epsilon, and this is L minus epsilon, and I want to guarantee that the values are this close to L. Can I do that? Yes. I can find a delta neighborhood. There it is. It's going to be a smaller neighborhood. But there it is. Now this is A minus delta and A plus delta. And now if x is in this smaller delta neighborhood, here's x now, then f of x is going to land in this smaller epsilon neighborhood of L. But it's true for any epsilon. I can now take an even smaller epsilon and guarantee the f's to be that close to L. And I can take an even smaller epsilon and guarantee for x's very close to A, for the f of x's to be very close to L. So using that for every, which allows me to take smaller and smaller and smaller epsilons, that's how I capture the dynamics of the limit property. So that's the idea of the... Now, if you try to just look at this picture the way it eventually came out, it doesn't say that much. Okay, it's how I drew it on the board, how it showed up, which more suggested what the dynamics are. Okay. So let's read the definition again. We say that the limit of f is L as x approaches A if for any epsilon there exists a delta such that being delta close to A, you should understand why I read this as being delta close to A implies f being epsilon close to L. Okay? Let me add one little detail here. Remember that we said that we don't care about the value of f at A itself. All we care is what happens as we get closer and closer. Okay? So that's going to explain why I add here greater than 0. This greater than 0 that I just added rules out the possibility of x itself being A. Because if x is A itself, then A minus A is 0. But we're only saying this for differences greater than 0. Okay? So this just rules out x being A itself because we don't care what happens at A itself. And in blue here, I might add x between A minus delta and A plus delta, but not equal to A. It's very small here, but what I wrote here is not equal to A. So that's just a final touch to make this entirely accurate. So I'm going to let you ask some questions now, but I have to say this. This definition is heavy. It takes time to get used to. It takes time to absorb, let alone to really work with it and prove things with it. We're going to do that. We're going to do some of that, but only to a certain extent, because this is not the mathematician version of Calculus 1. So we're only going to kind of get acquainted and hopefully not be afraid of it, but we're not going to really get into the heavy proofs using this definition. We're just going to see how it builds up the very first things and then continue from there. Okay, questions? Yes?
It seems like you're using the limit of epsilon approaches 0 to define a limit.
No. The question was, it seems like I'm using the limit of epsilon approaching 0. But that's exactly what I'm not doing. I'm using the for every. Okay? And the for every is not a limit phenomenon. It just says for every epsilon. Take an epsilon. 2, 1/2, pi, 1 over 17. Not negative 1, because it has to be positive. Okay? Take any epsilon, this property here will hold. Okay? So that's why I emphasize this word for every. Okay? More questions? Yes?
If it has got a jump,
You have to raise your voice a bit.
if it has got a jump at point A,
If the function has a jump?
jump discontinuity.
Okay, so the question is, what if it has a jump discontinuity? So we don't know what discontinuity is yet, let alone what discontinuities are. And in particular, we don't know what jump discontinuities are. Okay, so we'll get to that. We'll get to that. That's where we're heading. But as for your question, without using words that we don't know yet, I know some of you, of course, do know those words, but we're going to only use words we learned already formally. So if you look at the picture, if the function has a jump, if the situation is, please look at this board again, if the situation is something like this, where the function has a jump, please look at this board again. If the situation is something that has a jump, then it's not going to be true that if you want to be epsilon close to any value, you can guarantee that by being delta close to A. Okay, if this is the point A, if this is the point A, there is no neighborhood you can take of A, no neighborhood. I'm starting to exceed the limit of what I can put between my fingers with all these. Let's throw you away and you away. So there's no way we can guarantee, no matter how small a neighborhood we take of A, we cannot guarantee all the x's being close to some value. There are always going to be x's up here, and on this side there are going to be x's down here. What does it mean? It means that the limit doesn't exist. For this function at a point A, if this is the picture, it does not have a limit. Okay? And we're going to discuss various cases where limits don't exist. One of them is going to be when there's a jump like this, but it's not going to be the only case. There are going to be more cases where there's no limit. One comment I want to make is that in putting this drawing, I cheated you a bit. I made the drawing nice and symmetric to make it easy to understand. But in fact, by doing this, right, we said for any epsilon down, there's a delta such that if you go up, you land here. I made everything nice and symmetric. But if the function, for example, so let me erase this. On the side here, we're going to... If this is A, and the function was something maybe that looked like this, maybe something like this, there's still going to be a limit, okay? The limit is still this value here, but if you try to do this pictorial kind of dynamics that I represented, you'll see that from the left side, in order to guarantee being close to this value, you have to get the neighborhood you need here of A is not symmetric. Okay? If you take a neighborhood like this, that guarantees this distance from the candidate for L. But if you take a neighborhood, a symmetric neighborhood on this side, you get this close to this candidate for L. Do you see that? So if you want to get a symmetric neighborhood, we take the smaller of the two. So if we want to, for example, be this close to L, we have to take a neighborhood which would guarantee it on both sides, and we'll need something like this.
We should start from the Y.
Right. If we want to be this close to L, we're going to start from the Y. We're going to get here. We're going to land here. So this is not going to be relevant. So the picture we're going to get is something like this. But this is not a symmetric neighborhood, right? This neighborhood is not symmetric about A. So we're going to have to reduce it to here and take this as the delta neighborhood, which guarantees, although we kind of left out some things that would have worked. Okay? So this is just a side comment. It's not very important because we're not gonna get too deep into the details of this definition. This definition is a real challenge. A real challenge. Okay, more questions?
Yes. I understand from here that if I choose X on the neighborhood of A, I will get inside the neighborhood of L
Exactly.
for all epsilon. But where it's writing that I'm going to get approaching, I'm going to get closer. And
That's
closer
it.
to
The for all is what does that. For all is saying, take epsilon big in orange. See it? See epsilon big in orange? There it is.
It shouldn't be like really small.
Wait. You want to see the getting close to, right?
Yes.
So I'm saying it's hidden in the word for all epsilon. Take epsilon big in orange. Can you guarantee landing in this big in orange neighborhood of L?
Yes.
Yes, you can. Okay. Now take epsilon smaller and red. Can you guarantee landing in this smaller or red neighbor? Wait. You have to say yes now.
Yes.
Yes. Take epsilon even smaller. Okay. And yellow. I don't have a yellow marker. Can you guarantee landing in this smaller or yellow neighborhood? Yes. For any epsilon, you can guarantee this. And that for any is saying you can get as close as you want to this value L by taking x's closer and closer to A. For any epsilon, there's going to be a neighborhood of A which guarantees landing here, which guarantees being close to this. You want to get closer? You're going to need to get closer to A. That's what's hidden in that for any epsilon. Okay? It takes time. You have to think about this definition more and more, and we're going to do some work with it. Okay? It takes time to grasp it. There's genius people behind this definition, not just you and me. Yes?
The delta epsilon thing seems to me like more the definition of when a limit exists than the exact definition of the limit itself.
No. This is saying that the limit of x is L as x goes to A is all this statement. If this statement doesn't hold,
Then it doesn't exist.
then the limit doesn't exist. Yeah.
But this doesn't describe the process of finding the limit. It just describes the condition that there is a limit.
It defines what it means to have a limit. Okay? How to find limits? Well, the process is going to be the following. Step 1, we're going to calculate some limits with bare hands, using this definition, we're going to sweat. It's not easy. But we're going to do it for a couple of examples so you can appreciate how not easy it is. Okay? Then, using the definition, we're going to formulate some rules of how to find limits once you know some given limits. Okay? So if you know the limit of a function f and you know the limit of a function g, you know the limit of f plus g. You add them. Okay? So once we have these rules, we're not going to have to always resort back to the definition. We're going to use these rules. And eventually we're going to build up to the ultimate statement that we're going to have. Maybe I'll just put a huge spoiler on the next board, okay, and tell you what the ultimate theorem for limits is going to be in this context. And it's something you know. You know what I'm going to write now. Okay, so spoiler, beware. Okay, I'm ruining all the excitement now. But you know this. You know this. You know how to calculate limits, right? You've calculated limits before. But the statement is, we will see that if f is an elementary function, remember that notion? All those 8 families of functions and everything you can derive from them using the operations on functions, composition, division, subtraction, and so on. Remember? So almost all the functions that you know are elementary functions. This really leaves out only weird things like Dirichlet and the step function, and right? If f is an elementary function defined at A, so here we need it to be defined at A itself, then the limit of f as x approaches A is what? Is f of A. So for all these functions that almost all the functions you've ever encountered, if you want to find the limit, you just plug A into here. And that's how you've calculated limits, right? So we'll see that, okay? But it'll take time because we want to build to it, okay? We want to see how this, how we get something like this from that definition, which looks, I don't know, to me, these 2 boards look, one is in English, the other is in, okay, I know you guys are from all over the world, but in some language you don't know, right? This definition is challenging, okay? And in particular, we're going to later resort to this definition to define many more notions. I've mentioned that. Derivatives are going to be defined from limits. Continuity is going to be defined from limits. Integrals are going to be defined from limits. Almost everything in analysis somehow stems from the definition of a limit. Okay? Let me start doing some examples, okay? And then I'll take more questions.
Just one question.
Are we going to prove this as a theorem? We're not going to prove it in full detail because some parts here take work that is beyond what you need to know in this course, okay? But I'm gonna convince you that this is true, okay? We're gonna kind of put the guidelines for the proof, and you're gonna believe me that this is true, okay? But it's not gonna be today. It's gonna take some time. Okay. So let's move on with this definition of the limit. Let's do some examples. Okay, examples. So I want to find the limit as x approaches 3 of the function x minus 1 divided by 2. Okay, you know how to do this. The spoiler is already on the board. What is the answer? 1, right? I just plug in the 3. 3 minus 1 is 2, divided by 2 is 1. We know that this is the answer, right? But I don't want to calculate it now using things that I know. I want to prove this using that epsilon delta definition. Okay? I want to show you how not trivial working with that definition is. So I want to show that for every epsilon, there exists a delta such that if f of x, this is f of x now, minus L, this is L now, is less than epsilon whenever x minus a, 3 is a, is less than delta. That's what I want to show. Do you agree? So I want to show that f of x minus L is less than epsilon. So this is the way I usually work. I start by saying, let epsilon be greater than 0. Come on. Challenge me. Throw an epsilon at me. I'm ready. Okay? No, you can't say 1, because that's giving a specific epsilon. Throw any epsilon at me. That's let epsilon be greater than 0. You can say 1, and you can say 17, and you can say 1 over 100, and I'm ready for you. Whatever I'm going to write here is going to work for any epsilon you throw at me. Okay? Clear? So this let epsilon be greater than 0 is saying for any epsilon what I'm going to write is true.
Why it can't be negative? Why it can't be negative?
That's the definition. I want to show that whatever I wrote in the definition holds. You see, the definition says I only have to show it for epsilon positive. Okay? And now, what do I want to show? I want to show that f of x minus L is less than epsilon. My way of facing the challenge is to write what this is, start working with it, and I'm going to see how to proceed. It's going to kind of appear. So let's write it. What is f of x minus L? F of x is this. This is the function, right? So it's x minus 1 over 2. Do you agree that this is f of x? Minus L. What is L here? 1. So I want to show that this thing is less than epsilon. Good? Okay. Now what? I don't know. Let's do a common denominator. It's kind of the next step, right? I really flow. I let it lead me. So what do I get? So the common denominator is going to be 2. It's actually going to be the absolute value, but 2 in absolute value is 2, right? And on the top, I'm going to have x minus 1 minus 2. Do you agree? So on the top, I'm going to have x minus 3. Do you agree to this equation that I just wrote? Everybody? Okay. Again, what am I doing? What do I want? I want to say this is less than epsilon, right? If this is less than epsilon, then this is less than epsilon, and that's what I wanted to show. That's the definition on that board, right? So how can I guarantee that this thing is less than epsilon? Let's write less than epsilon, but this I don't know yet. This is what I want. Right? How can I guarantee that this is less than epsilon? Is it always going to be less than epsilon for any x? The answer is no. That's missing the whole point. Okay? It's not going to be less than epsilon for any x. It's going to be less than epsilon only for x's sufficiently close to a. What is a? 3. So a is 3. X goes to 3. So this is going to hold only for x's which are close enough to 3. How close to 3? Delta close to 3. That's what I need to somehow answer for this let epsilon be greater than 0. That's the answer I need to throw back at you. You throw at me an epsilon greater than 0, imagine tennis. I need to throw back at you a delta that will do the trick. Okay? What does that delta have to satisfy? That x, if x minus a, there it is, when I see this I'm happy. If x minus a is less than delta, then this thing has to be less than epsilon. Can somebody already see what that delta is going to be? Very good. Very good. So let's write it. So I'm going to add it up here. Let epsilon be greater than 0. Take delta to be equal to 2 epsilon. Of course, delta depends on epsilon. If you give me epsilon equals 1, delta is going to be 2. If you give me epsilon equals 1 over 1,000, well, delta is going to be small as well. It's going to be 2 over 1,000. Take delta equals 2 epsilon. Then, if, let me erase this want thing, which is in my way now. If x minus 3 is less than delta, then if x minus 3 is less than delta, then this equals this equals this. X minus 3 is less than delta, so this thing is less than delta over 2. Do you agree? And what was delta? Delta was 2 epsilon. 2 epsilon over 2 is epsilon.
So we just proved that the limit exists.
No! We just proved that the limit of this thing as x goes to 3 is 1. Not just that it exists, that it's 1. That 1 is the limit. Okay? Tell me before you ask questions if you agree to the following 2 statements. 1, it's hard to think of an easier example than this. Well, unless you take a constant function. But this is almost the easiest example you can come up with. Do you agree? 2, this was not easy. Right? So, this definition is challenging. Questions?
I didn't understand how we knew it was going to be delta equals to epsilon.
We didn't know it a priori. We started working with what we want to show. Okay? Just did some algebraic steps, got to here. We knew we want this to be less than epsilon, because that's what the definition calls for. And we knew we have control over this thing, x minus a. That's the definition. Look again at the definition. Let's look at the definition again on this board. We have control over x minus a. That's what we can handle. Please look at this board again. Hello. Please look at this board. We have control over x minus a. That's the x minus 3 in the example. We want to show, this should allow us to handle f of x minus L. F of x minus L we got over there. We want it to be less than epsilon by controlling x minus a. Going back to the example, this is what we got for f of x minus L. If x minus 3 is less than 2 epsilon, then x minus 3 over 2 is less than epsilon.
Why you take the 2 out? I'm saying like 2 should be part of the x minus a.
What 2? No, x minus 3 is less than delta.
Why x minus 3 and not x minus 3 over 2?
Because it's x minus a.
What is it?
A is 3, so this thing is x minus a. I can only say something about the distance from x to a. Good? Let's do another example. The 2 just appeared in the calculation.
Exactly, the 2 epsilon.
Put 2 epsilon here. You get epsilon when you divide by 2. Do you see that? Okay, let's do another example. Let's just do quickly another example. This takes time to absorb. I'm not saying it doesn't, and absorbing it should make you appreciate it. Okay? Wait. Let's do another example and then more questions. Absorbing it should make you appreciate it. Okay? And we're not gonna dwell on it too long. We're not gonna prove every single theorem using the definition. I just want you to kind of get the flavor, okay? And in particular, to understand that it's not that easy to work with. You get used to it, though, okay? Another example. Wait, another example. Let's do the limit as x goes to a. Here, a is going to be any number. It's not going to depend on what a is, of sine of x. What do we expect the answer to be? Sine of a. Right? It's an elementary function. We expect this to be the answer. Do you agree? And you can write here 5 if you prefer, but it really doesn't depend on what a is. For any a, this is going to be true. Right? Let's prove it using the definition of the limit. Let epsilon be greater than 0. Leave some blank space where we'll fill in the details. Take delta to be blah, blah, blah. And what we're going to show is what is f of x minus L. F of x minus L in this case, what is f of x? Sine x, that's the function. What is the limit? Sine a. We want this to be less than epsilon. Okay? How can we continue from here?
Finding delta.
How? How are you going to find delta? Remember, what you can work with is only when you see x minus a. X minus a, that you can control with delta. More ideas? Very good, very good. Remember I told you, I don't expect you to remember all the formulas by heart, but I do expect you to remember that they exist. And when you see a difference of signs, you should remember, wait, I know, there's a formula for that. Let's look it up quickly. There it is. Okay, so here's the formula. So I'm going to replace, the formula for the difference of signs is 2 times the sine of the difference divided by 2 times the cosine of the sum divided by 2. That's the formula. That's a known trig formula which you can look up. Okay? And I'm happy to see this because there's x minus a. There's something I can feel comfortable with because I know x minus a, that is going to be governed by delta. Okay? Good? Wait, let me finish the example and then questions. Okay. So the absolute value of a product is the product of the absolute values. So the 2 I don't need an absolute value on again. Sine x minus a over 2 times cosine of x plus a over 2. Okay. Now I'm going to do 2 things. So first of all, this is going to be less than or equal to whatever I write here. But that's okay. If it's less than or equal something, which eventually is going to be less than epsilon, then the whole thing is less than epsilon. Do you agree to that? Okay. So the first thing I'm going to do is I'm going to altogether drop this and say this is cosine of something. Cosine of something is always less than or equal to 1, whatever that something is. Do you agree? So that's one thing I'm going to do. Cosine of whatever is always less than or equal to 1 in absolute value. Do you agree? But that's not what I'm using. I'm using the fact that it's less than or equal to 1. So this is going to disappear because I'm going to replace it by 1. The other thing I'm going to do in this step is sine of something in absolute value is always less than or equal just the something in absolute value. This we don't know yet. I'm just saying it. We're going to prove it. Okay? But there's a place where it's very natural to prove that fact. And you're going to believe me now, I hope. I'm usually an honest guy, and trust me. But all the people that lie to you always say, trust me before, right? Okay. Believe me on this one. But we're going to prove it. Okay? So the next thing I'm using here is the fact that sine, let's call it alpha. So sine of alpha in absolute value is always less than or equal to alpha itself in absolute value. Okay, so this fact I have a debt here. I'm going to prove it a bit later. In radians. We're always working in radians. Okay, so what I get here is this 2. Instead of sine of this thing, I just write the thing. So I get x minus a divided by 2. I replaced sine of this by just the argument. And that's it. The 1 replace this. So believing this, do you agree to this step? Everybody? Okay. And now the 2's cancel out, so I just get x minus a. What do I want? I want this to be less than epsilon. Is x minus a always less than epsilon? Not for every delta. No. Careful, careful. The for every and the for all are very delicate here. I want to be able to write this is less than epsilon. How can I guarantee this? Right. Take, in this case, delta just to be equal to epsilon.
That's the part where you're proving? They take...
Yeah. I have to... The definition says the following. Back to the definition. Look on the board here again.
Now you plug these values.
Wait. Look on the definition here a second. Look on this board. For every epsilon, there exists a delta such that blah, 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 blah. Okay? In order to prove it, I have to show that given an epsilon, I can provide a delta. That's what I need to show, right? Such that this holds. That's what I'm showing. Given an epsilon, back to the example, given an epsilon, I need to show a delta that would guarantee that if x minus a is less than delta, then f of x minus l is less than epsilon. Through all these steps, I found that f of x minus l is less than or equal to this thing. So if this is less than delta, and delta equals epsilon, I'm done.
So by doing that, you're proving...
Yes, I'm actually proving this fact. Okay? So take delta, let me just finish it off. Take delta equals epsilon. Then, if x minus a is less than delta, we should add the greater than 0. I forgot it on the previous board. Let me do that too. If x minus a is less than delta, then f of x minus l dot 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 is this. This is less than delta. Delta equals epsilon. This is less than epsilon. Done. We proved that this limit exists and equals this L. Yes?
So for if it ended up that x minus a was over 5, then you would do L equals 5 epsilon, delta equals 5 epsilon.
Yes, for example. But in general example, so the question was if I got x minus a divided by 5, would I take delta to be 5 epsilon? Yes. But in right, I'm defining delta per epsilon. But in general, you can get very, very complicated things. Okay, the x minus a can be hidden. First of all, can be hard to get to. Okay, when you're at this step, it's not clear how to make x minus a show up, right? Only if you think of using this formula, then you suddenly see it, and still you have to do some things, right? And in general, it's going to be not easy to get to this x minus a. And on top of that, this x minus a might be hidden among all kinds of other expressions which you have to somehow argue and control for. Okay? So these are like the easiest examples, and I don't know if this makes you happy or not, but we're not going to see much harder examples. So, because this is just a calculus course not for mathematicians. Okay? Yes?
So, in order for the limit to exist, just to clarify an earlier question, there has to be a function that relates delta to epsilon, or not
Right.
necessarily?
You can think of delta as a function of epsilon. That is perfectly true. Delta depends on epsilon. When you start off with an epsilon, that delta is going to depend on it. If epsilon was big, if you wanted to guarantee only being that close to the limit, usually a big delta would guarantee it. If you want to guarantee being very close to the limit, usually you need a very small neighborhood of x. And usually that dependence between delta and epsilon, in most cases, except for very, very special cases like a constant function or something like that, delta is going to be some function of epsilon. Here it was just delta equals epsilon. In the previous example, it was delta equals 2 epsilon. And in general, it can be anything.
And are we going to
Okay.
do an example of showing that it's the limit, that it's not the limit?
Yes, we're going to do wait, hold your horses. We're going to do examples showing that examples in which the limit does not exist. Like somebody mentioned one before, like when you have a step. Okay, we're going to discuss those. Okay, we just learned to walk. Okay, we just stood up. We're still learning to walk. Okay, this is not easy stuff. Let's have a break now. You can ask me more questions over the break, and we'll continue afterwards.
You take me?